Okay, so I'm going to make this video to go over the Topic 7 Review Questions worksheet. Question 1, it says photons of energy 2.3 eV are incident on a low-pressure vapor. The energy levels of the atoms in the vapor are shown. Here they are. And notice, just as kind of an aside, it says not to scale. The reason for that is that, as you should recall, the spacing between the levels changes as you go up from the ground state down here up to the ionization energy level. So this is clearly not drawn to scale. It says what energy transition will occur when a photon is absorbed by the vapor. And so the key concept here is that that the electrons in this low pressure vapor are capable of absorbing photons of just the right amount of energy. And so photons can be absorbed as long as the energy of those photons is equal to the difference between two energy levels. So just for example, the photons that would be capable of being absorbed would be, let's say, 1.6 eV photons, because those would be able to transition electrons from the negative 1.6 eV up to the 0 eV level. Other photons that could be possibly absorbed, and again I'm looking at the difference between two energy levels. The difference between these two energy levels would be 0.9 eV photons. Those photons would be possible to be absorbed. Also 2.5 eV photons from the negative 2.5 level up to 0, 3.9 eV, 1.4 eV, and so on and so forth. And all other photons that are incident on this vapor are just going to pass straight through the vapor. And so they're not going to be absorbed. The electrons ignore them. And so it's only these kind of specific photons that are capable of being absorbed by the electrons in the atom. Also, 2.3 eV photons from the negative 3.9 up to the negative 1.6 are also possibly absorbed by this vapor. So when electrons are absorbed, what happens? When photons are absorbed by electrons, what happens is the electrons gain energy. Right? They kind of suck the photons out. They suck the energy out of the photons, and they use that energy to transition up to a higher energy level. And so in this case, we know that because the photons are being absorbed by the vapor, we know that must correspond to an upward transition. And if you look at some of these answer choices, for example, D represents a downward transition. And so D is out. C also represents a downward transition. And if the photons have an energy of 2.3 eV, the only way they will be absorbed is if an electron is able to transition between two levels, and the spacing between the two levels has to be 2.3 electron volts. And so that is going to be A. B does correspond to photons being absorbed, but those would correspond to photons of energy 1.6 eV, not 2.3 eV. So the correct answer there is A. And if we move on to 2, when an alpha particle collides with a nucleus of nitrogen-14, a nucleus X can be produced together with a photon. What is X? So this is kind of testing you on a couple things. Number 1, what is an alpha particle? An alpha particle is a helium nucleus. And so the way we would write that would be like this, or like this. And so if we want to represent an alpha particle colliding with a nucleus of nitrogen-14, the way we would do that is we would say, let's say 4 to alpha plus, the plus meaning combining with or colliding with nitrogen-14, and what is produced as a result of that collision? Some nucleus X, which we're trying to find, plus a proton, and a proton has the numbers 1, 1, and P for proton. And so if you can understand that this is what the question is asking, and set it up like this becomes a very easy question to answer, because we know that mass number has to be conserved on the top, and we also know that atomic number has to be conserved on the bottom. And so on the left side here we have 4 plus 14 is 18. So what number plus 1 gives you 18? That must be 17. By the same token, 2 plus 7 minus 1 gives 8 over here, and so x has to have the numbers 17, 8. That means the answer is B for number 2. Okay, moving on. Question 3, the mass defect for deuterium is 4 times 10 to the negative 30 kilograms. What is the binding energy of deuterium? And so when we talk about binding energy, we're talking about the difference between the nucleons and the nucleus. And so for deuterium, that mass defect, I should say that's one type of mass defect. That mass defect is 4 times 10 to the minus 30 kilograms. And the reason the mass defect exists inside the nucleus, or I should say inside the atom, is because when the nucleus is assembled from the individual nucleons, in this case deuterium is this particular isotope of hydrogen. When that proton and that neutron assemble together into a nucleus, they lose some mass, and the reason they lose some mass is because some of that mass is used to is basically converted into energy, and that energy is called binding energy. And so we know how much mass was lost, and we want to find out how much energy is that mass worth. And so that's where we go back to Einstein's famous equation, E equals mc squared, right? If we know this much, if we have this much mass, we can find out how much energy is that mass worth. In this case, that's binding energy. And so we're in SI units. So 4 times 10 to the negative 30 times c squared. Now c is the speed of light, and c has a value of approximately 3 times 10 to the 8 meters per second. And so that means c squared would be about 9 times 10 to the 16 meters squared per second squared. And so if you just kind of look at the numbers we have here, the answer we're going to get here, because we're in SI units, is in joules, and that's going to come out to be approximately, let's see, 36 times 10 to the negative 14 joules. Okay, and if you were to convert that in joules to electron volt, 1 electron volt is about 1.6 times 10 to the 19 joules. If you do that conversion, then the answer you get becomes obviously some number close to 1,000,000, just looking at the orders of magnitude on here. And if you look at the answer choices, there's only one answer choice that's close to 1,000,000, and that's going to be C. Remember, on multiple choice questions on the IB exam, you can't use a calculator, and so even if you get to this point and you can't do these calculations, well, you don't really need to, as long as you just, kind of make an order of magnitude approximation. Forget the 36, and just look at the 10 to the minus 14 over 10 to the minus 19. Your answer should be somewhere around 10 to the 5-ish. The actual one is about 10 to the 6. And there's only one answer choice close to that. That would be C for question 3. Question 4, moving on, which of the following lists the particles emitted during radioactive decay in order of increasing ionizing power? Alpha particles have the highest ionizing power because they are the biggest and most massive particles, and beta is in the middle. Gamma has the lowest ionizing power, so the correct answer for 4 is A. Okay, question 5. It says a simple model of an atom has 5 energy levels. What is the maximum number of different frequencies in the emission spectrum of that atom? Well, so I'm just going to kind of draw out some different energy levels here. So let's say this is a ground state, n equals 2, 3, 4, 5. And remember that in the emission spectrum corresponds to photons being emitted from the atom, and photons are emitted when electrons experience a downward transition in energy. Okay, so for example, if we have an electron transition from the n equals 5 level to the n equals 4 level, a photon is going to be emitted, and the energy of that photon is going to equal the difference between those two energy levels. And so when it says what is the maximum number of different frequencies, each possible downward transition corresponds to a unique frequency in the emission spectrum. And so if you understand that, all you have to do is count out the possibilities of the different types of emissions. For example, n equals a transition from n equals 5 to ground state, like this, is one frequency. Now, this is corresponds to a second frequency, and a third, and a fourth, and we just kind of have to go on like this. Here's another. I'm just going to kind of write these out. And so these are all the possible downward transitions that might result in a line appearing in the emission spectrum. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different possible downward transitions. That's 10 different frequencies in the emission spectrum. And so the answer for question 5 should be 10. I believe that is C. So I'm going to erase this. I believe question 5 is C. Moving on. Question 6. Which of the following is the correct definition of the binding energy of a nucleus? This is really a definition question. And you need to be careful because there's two different definitions for binding energy. Okay, and so one possible definition for binding energy is the work required to completely separate the nucleons from within a nucleus. Okay, and so looking at the answer choices, B is the correct answer. The other definition of binding energy is the energy released when nucleons assemble to form a nucleus. Okay, and so keep in mind there's those two definitions for binding energy. In this case, B is the correct answer, though. Question 7, we have some energy levels. The atom is excited, and remember, excited just means that instead of the electron living in the ground state where it wants to be, if it's excited, that means the electron is at some level above ground state. So n equals 2, n equals 3, n equals 4, some other energy level other than n equals 1. So this atom is excited, so an electron is promoted to the negative 0.5 eV energy level. How many different frequencies will be observed in the emission spectrum? That's just the exact same question that we just did. And so this is really just a matter of counting out the number of possible downward transitions from the negative 0.5 eV level. So there's 1, there's 2, there's 3, there's 4, there's 5, and there's 6. So from n equals 2 to n equals 1 would be the 6. So the answer is D for question 7. Okay, moving on to question 8. The initial number of atoms in a pure radioactive sample is n. The radioactive half-life of the sample is defined as... So, first of all, half-life is measured in time, which is why the symbol for half-life actually is T, 1/2. That eliminates B and D. And by definition, the half-life of a sample is the time it takes for half of the previous amount to decay. So, if you know that, the correct answer should be C. Okay, moving on to 9. In a neutral atom, there are any electrons, Np protons, and Nn neutrons. What is the mass number of the nuclide? Mass number is defined as the number of nucleons within the nucleus of an atom, and so that would be the number of protons plus the number of neutrons. That would make the answer B. Electrons have nothing to do with mass number. Question 10, binding energy per nucleon of hydrogen 3. Nucleus is 3 MeV. What is the minimum energy needed to completely separate the nucleons of hydrogen 3? By the way, that is also called tritium. And so, if you understand that the minimum energy needed to separate the nucleons of an atom is basically the definition of binding energy, then this question is really just asking what is the binding energy. So, we're given that the binding energy per nucleon is 3 MeV, and in hydrogen 3 we have 3 nucleons, because the mass number is 3. So 3 MeV per nucleon times 3 nucleons gives a binding energy of B. So this is another example of why definitions are important, because if you don't recognize that this question is basically restating the definition of binding energy, then you can't answer the question. 11. Which of the following provides evidence for the existence of atomic energy levels? Atomic spectra. Right, and so that's one of the things that was unexplainable by the Rutherford model of the atom. When you get to Bohr's model of the atom, Bohr, his model, even though it's not 100% kosher, it's still able to explain the existence of atomic spectra. Okay, moving on to 12a. It says a nucleus of phosphorus 32 decays by beta minus decay into a nucleus of sulfur 32. The binding energy per nucleon of phosphorus 32 is given, and it's also given for sulfur 32. Determine the energy released in this decay. So to do this question, we need to first be able to write out this decay reaction. And so we start with phosphorus 32, and phosphorus 32 undergoes beta decay and becomes sulfur 32. So here is the daughter nucleus. We also have beta minus, and remember with beta minus we always have an anti-neutrino. Okay, so basically what's going to happen is there's going to be a difference in binding energy between the product side and the reactant side, and the difference in the binding energy corresponds to the energy being released in this reaction. So the binding energy on the left, the binding energy is going to be that 8.398 MeV times the 32 nucleons, and for the sulfur, the binding energy is going to be a little bit more, that 8.450 MeV times the 32 nucleons. You might say, what about the binding energy of the beta particle and the antineutrino? Well, those are not nuclei, so they don't have binding energy. And so, if we calculate this out for phosphorus, the total binding energy is going to be about 268.736 MeV, and for sulfur, the binding energy is going to be approximately 270.400 MeV. And if we just look at the difference between those values, we find that the energy released in this reaction, which corresponds to the difference between these two binding energies, that the difference there is about 1.664 MeV. And so that corresponds to how much energy is released in that reaction. Okay, take a moment to look at that. Okay, question 12b. The graph shows the variation with time t of the activity A of a sample containing phosphorus 32. determine the half-life of phosphorus-32. So activity, if you recall, activity is basically the rate at which the decay is happening. And so the activity half-life is the same as the actual half-life of the radioactive substance. And so in this case, if we see, for example, how long does it take to decrease by half? Now the initial activity, which I'm going to call A0, is approximately, let's see, if you go by this graph, approximately 480 BQ is the unit for activity is the becquerel. It's no longer a unit you need to know, I believe, but that is the official SI unit for activity. And so basically, if we want to know the half-life, what we need to find is how long does it take to get down to 240 becquerel. And so from the graph, 240, 1, 2, 3, 4, we go over, that takes approximately 11, 12, let me just scroll down so I can see the units, approximately 12 days. And so the half-life here is about 12 days. Let me change that. Half-life is approximately 12 days. And keep in mind, if we hadn't started at the beginning, if we had picked any other point and measured the time that it took the activity to decrease by half of that amount, we'd still find 12 days. Okay, moving on. 13, outline how the evidence applied by the Geiger-Marson experiment supports the nuclear model of the atom. That's something we spend a lot of time talking about in class, so I don't want to belabor the point. You should have that in your notes. 13b, outline why classical physics does not permit a model of an electron orbiting the nucleus, because basically classical physics, going back to the Rutherford model of the atom, in classical physics, if you have accelerating charge, such as an electron circling around the nucleus, that charge should radiate energy. And so, in classical physics, if you believe classical physics, the electron, as it orbits the nucleus, should radiate energy and spiral into the nucleus. And so, since that obviously doesn't happen, the solution is that classical physics must be wrong, at least in the case of things that are very, very small, like atoms. State what is meant by the terms nuclide and isotope. Nuclide is just a specific, I guess, a specific type of nucleus. For example, I don't know, hydrogen-3 is a nuclide. Carbon-12 is a nuclide. Isotopes specifically refer to when you have one specific element with different numbers of neutrons. Those are isotopes of that element. And what makes an isotope, for example, you have 3 isotopes of hydrogen, hydrogen, deuterium, and tritium, and the difference in isotopes is they have the same atomic number, but different number of neutrons, and so they have different mass numbers. So that is what is meant by isotope. And finally, 13d, construct the nuclear equation for the decay of radium-226. This just goes back to, again, understanding that, first of all, the helium nucleus is an alpha particle. Those numbers are 4, 2. Gamma, this is the symbol for gamma, has no atomic numbers. And once you know that, it's just simple math to figure out the rest, keeping in mind that you're not given a periodic table on the IB physics exam. Okay, so that is 13d. And the last question, radium-226 has a half-life of 1600 years. Determine the time in years it takes for the activity of radium-226 to fall to 1/64th of its original activity. And so, to do this type of question, really what we need to find is 1/64th, how many half-lives is that? And so, I guess the most basic way to do this is to kind of count it out. 1 half-life would correspond to the activity be decreasing by a half. 2 half-lives would correspond to the half-life decreasing by a fourth. Let me kind of partition this off here. 3 half-lives would be an eighth, and so on and so forth. And we can just kind of count this out. 132, 6 is 1 over 64. And so, I don't know what that line is. And so, after 6 half-lives, we've decreased to half of the original activity. 1 half-life is 1600 years, and so the answer to the question is just 1600 times 6, which is approximately, I believe, 9600 years. Okay, so after 9600 years, the amount of radium-226 that you had to begin with has fallen to 1/64th of its original amount. So that does it for topic 7 review questions. Let me know if you have any other questions, please.